So with yesterday's little activity on molecular geometry yoga, which worked out pretty well, that kind of brings us to the end of analyzing shapes of molecules. And so to finish off this particular unit, we now want to apply those shapes to studying ultimately the intermolecular forces, how different molecules interact with each other. And that's really the primary goal of this particular unit, to talk about properties of matter, again, whether certain molecules are existing in the solid state, liquid state, gaseous state at room temperature, and why those particular molecules behave the way they do. So this is the second part of that analysis. First part is the shape, and the second part is how does that shape then affect the polarity of the molecules. Again, this is very much review from last year. I probably go into more detail than I need to when I teach you this concept in grade 11, which makes this should make this flow fairly easy when we analyze it this year. So again, no need to write this down, but initially we need to talk about polar covalent bonds, and that has everything to do with the delta En, right? The electron pair is shared unequally between the nuclei of two atoms if they're polar. The shared pair of electrons spends most of their time closer to the atom with the higher En. And again, I guess that's not a new interpretation. In our quantum idea, right, we've got this probability of finding the electrons. And in our Lewis idea, we've got this line that represents the two electrons. So last year, I would have stated the one with the higher electronegativity just would pull those two electrons closer to it. Now in the quantum representation, we think of it actually kind of changing the shape of that electron density, of that area where we're going to probably find the electron. And so it simply means that the higher electronegativity will pull that orbital, that molecular orbital, in such a way that it'll be deformed closer to the one with the higher electronegativity. So it becomes more probable to find the electrons closer to the atom with the higher electronegativity. Again, either way, it results in the same thing. This results in the formation of dipoles, regions of partial positive and partial negative charge. Again, very much like last year. And again, we have that delta En. If the difference is between 0.2 and 1.7, then we say that it is polar. And there's the bonding continuum there. And 0 to 0.2 non-polar covalent bonds, polar 0.2 to 1.7, and 1.7 greater is ionic. And as I stated yesterday, the textbook, if you read through those pages, you'll notice it says 0 to 0.5 is non-polar. We'll stick with the 0.2 for this year. That's what you guys have been going with. So when you're answering questions on the test, you can stick with that 0.2 to determine whether it's polar or not. Okay, so you can write this down now, because now we're going to apply this all to molecules. So the rest of the lesson now is essentially, how do we determine whether a molecule is polar or non-polar? Again, we did this last year. We did all of this stuff last year. Again, it's very much a review. But what we can do now is, when it comes to shape, we can actually determine the shape. We can determine the molecular shape using Vesper theory, and then from that, whether it's symmetrical or not, we can then determine whether we have a polar molecule or not. So let's start by describing nonpolar molecules. So a molecule is nonpolar if there's no permanent dipole moment on the molecule, and if we have something that is, diatomic especially, and made up of the same two atoms, the delta En is 0. In this case, there is no shift in that charge. It's completely equal sharing. We say it's a pure covalent bond, and there are no dipoles on that molecule, okay? No permanent dipoles. When we eventually get to talking about London forces, we've already learned that there are random fluctuations of that charge. If the two electrons happen to end up at one end than the other, then we get this very small dipole, right? Those are called the London forces, and that's what causes these nonpolar molecules to stick together, just kind of reviewing and looking ahead, I guess, at the same time. But for now, we're just talking about whether it's polar or not. Delta En is 0, equal sharing, no dipoles on that molecule. So a molecule will be nonpolar if all of the bonds are nonpolar, and that was what that first example was. And for the examples, you don't have to write down nonpolar bonds, therefore nonpolar molecule. We'll do that when we get analyzing some of the others. But F2, right, and I can draw it out. It's not a big deal. If you were going to analyze this, you might do something like this. You're going to look at that. You're going to say delta En is equal to 0, therefore nonpolar bonds, and therefore it's a nonpolar molecule. All right? Same with the pH3. If you're analyzing for polarity, I suggest you do what we did when we were doing the 3D Lewis structure, right? I would draw the Lewis structure. I would think about what its hybridization is. I would think about then what its molecular geometry is after I eliminate the electrons. And pH3, this is one that would be if I put the lone pair up top, this would be a sp3, right? H, H, H. But it really doesn't matter because the delta En, and when I had a different periodic table, the ENs for H and phosphorus are very close to each other. I think they're both 2.2, but I think on your table, phosphorus is something like 2.19 or something like that. If you could check it. If you got your periodic table nearby, get the periodic tables out because we're going to need to do some delta En calculations. 2.19, so it's something like 0.01 is the difference. It's approximately 0. So again, nonpolar bonds, nonpolar molecule. This thing would not be polar. All right? I don't want to spend a lot of time on this. I get the impression that this is very much review. Let me know if I'm moving way too fast on this. If I am, we can do it step by step. But I get the impression that this is very much review. Okay? So if the bonds aren't polar, then the molecule will not be polar. And then there's the second possibility. We can have polar bonds, but if the shape of the molecule is symmetrical and the dipoles cancel away, then we will also have an overall nonpolar molecule. So just put EG, examples, I was typing things out here. BeH2. Now again, like I said, if you're given a question like this on the test and asked to determine whether it's polar, et cetera, if you're unsure, count up the valence electrons, draw the Lewis diagram, et cetera, come up with the hybridization, you know, all the steps that we've gone through. Make sure you use those steps. For the sake of some speed here, though, I'm going to jump ahead, go right to the end. You might already be able to see that. If we're dealing with beryllium, hopefully we've done it maybe enough that beryllium, you know, is a special case. It's only going to need 2 bonds. It's got 2 H's on it. It's going to be sp hybridized. So we're going to have something that looks like this, BeHH. And that's my 3D Lewis diagram. So I'm going to jump right to the 3D Lewis diagram for the sake of getting done so you can work on some homework. And so this is a linear molecule. And if we calculate the delta En, again, we've got 2.2 for the hydrogen. And what is it for Be? What's the electronegativity for beryllium? What do you got? 1.57, 1.57. I'm not going to do that in my head because there's way too many little numbers in there and I'll mess it up. What do we have there for a subtraction? 0.63? 0.63. Remember, it's the absolute value. I'm not worried about the sign. And then again, we can say, therefore, right, polar bonds, right? This thing has polar bonds. The higher electronegativity is the hydrogen, which means my dipoles will head out towards the hydrogens. Arrow heading out to the H with the plus on the inside, arrow heading out to the H with the plus on the inside. And the other way in which we wrote this, slightly negative, slightly positive, slightly negative, if you recall. And because it's symmetrical and those dipoles are pointing in the opposite direction, we say they cancel out, all right? That's the quick chemistry way of saying they just cancel out. Mathematically speaking, because many of you have taken physics, what you have to do in order to determine whether there's an overall dipole or not is you need to do a vector addition of all the dipoles. And we need to then add those vectors up. And if the vectors add to 0, then you have a nonpolar situation. If you're taking physics, I think you know what I'm talking about. Let me just do a single diagram for this, and I won't do it again for the rest of them. But if I were to take this dipole vector, right, and then adding tip to tail, add the other dipole vector, because they're the same length, they're going to add to 0, and therefore we have no overall dipole moment because the two vectors add to a total of 0. Nonpolar molecule. Okay? All right? If you're not understanding that vector thing, because they're in opposite directions and they're the same size, they cancel out. Okay? All right. Some other examples, BCl3. Again, boron, special case, can have 3 bonds. There's 3 chlorines on this. It's going to turn out to be our trigonal planar, Cl, Cl, Cl. Again, delta En. What do you got there, Mallory? I'll take the 2 numbers and the total. What do you got? 2.04. Again, greater than 0.2, less than 1.7, therefore polar bonds. And I'm pretty sure the chlorine probably has the higher electronegativity. Is that the case? Yeah, so our dipoles are going to head out this way. They're going to be all the same length. And again, they're going to cancel out. And if you were to add those 3 vectors together, you'd get a nice little triangle that ends up back to the beginning, right? So it cancels away. So again, because it's symmetrical, and we can still do that. Remember, we were doing that last year. We can do it here as well. You're going to look at the picture. You're going to know that it's trigonal planar. That's symmetrical. And therefore, the dipoles cancel. And therefore, non-polar molecule. All right? Okay. Carbon tetrachloride. Again, carbon follows the octet rule. I need 4 bonds. We've got chlorines. If you have to add up electrons, by all means, do that. But this guy is carbon, and this is sp3. So we're going to have our perspective diagram, Cl, Cl, and Cl. Again, just for speed, I'm going to dispense from calculating the delta En. It is greater than 0.2, right? We've gone through all the steps. This one also, the chlorine has a greater electronegativity. I don't have it on this table. I wish I did. I'm pretty sure the chlorine has a greater electronegativity. Yeah. So in this case, our dipoles are also pointing out towards the chlorines. Again, that's where the negatives will be. And it might be hard to imagine, but this is also symmetrical, even though it's three-dimensional. You can think of the symmetry in a couple of ways. Number one, three-dimensionally, you can think of it as everything pointing totally opposite away from each other with the same angle. That means all of these dipoles will ultimately cancel out. Another way of thinking about it is if you look straight down one of the bonds, you almost see a trigonal planar type shape, which is symmetrical in the X and the Y, but they are pointing all down. So if you take those little Z components of each of these vectors, it'll cancel out the opposite side Z component. So it is symmetrical. I don't need you to do any fancy math or anything. You just need to think of the tetrahedron as being a three-dimensional symmetrical molecule, and therefore the dipoles cancel. So again, we can say here that this is symmetrical, therefore dipoles cancel, and therefore non-polar molecule. Okay, so symmetry cancels them out. Now, I would have given you some examples on that last year, but I would have stopped at that point. Other examples of nonpolar molecules, and you can write this all down, but I'm not going to draw them all out. If I were to have something like phosphorus pentachloride, and we were to draw it all up, it's sp3d. And I could just draw that to just give us a reference point. I think we called it AX, whatever, so I'm going to just bring it out like this. We'll go out front on this one and behind on this one. So if I have all the same atoms on that, I got an AX5. The trigonal planar in the equator will cancel away, because that's the same as trigonal planar, like with our boron. And then the up and the down guy will cancel away. They'll all cancel each other out. That's only true if all of the atoms are the same. As soon as you change an atom, you've got a different length dipole, and then it's not symmetrical anymore. SCL6, so in this case it's sp3d2. 1, 2, 3, 4, 5, 6. The octahedron has them pointing in opposite directions, all of them 90 degrees from each other. So opposite is all 180 degrees. All those vectors will cancel away. And again, you'll have nonpolar. Now, last year I would have told you a little trick to learn whether it's or to determine whether it's symmetrical or not. And I would have said, if there's a lone pair on the central atom, it's not symmetrical, because the lone pairs push the bonds around and change the symmetry, which is a true statement. Nothing wrong with it. It means that you could have answered questions on whether you had a symmetrical molecule without knowing the actual shapes of them. But there's a couple of little exceptions to that rule. Square planar, which comes from sp3d2, 4 bond pairs and 2 lone pairs. Remember, the 2 lone pairs have to go on opposite sides. If you have that situation, you've got the square planar in the middle, and that's also symmetrical. They will cancel out, and it will be nonpolar, even though it has 2 lone pairs on it. So that's an exception to the rule, but you don't have to worry about that in grade 11 because I never give you anything that's sp3d2 hybridized, because you don't know about orbitals and hybridization. But that square planar one, if you have your A, and then you've got 1, right, 2, 3, and 4, and then you've got lone pair and lone pair. Let's say we put them up and down, X, 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 and they're all the same, then those will also cancel out even though it has lone pairs. That contradicts my little shortcut rule that I teach you in grade 11. And if you extend that even more, put 2 more lone pairs on that, you've got the linear triatomic, it would also be, it would also cancel out. Okay? So there's the first one. The other one, it would be A. This time I'll put the lone pairs in the front and back position. And then you've got X and X. Also cancel those out, even though they've got lone pairs. Contradicts what we said last year. But this only works if we've got polar bonds and the identical atoms on the central atom. Now we'll talk about polar molecules where we either have non-symmetrical shapes or non-identical atoms on the central atom. Good to go? All right. So polar molecules. So again, as I would have stated last year, this is an AND situation. You have to have both requirements in order for it to be polar. You've got to have polar bonds, and you have to have a non-symmetrical molecule such that those dipoles do not cancel out. I've often considered trying to make this section a little more challenging for you guys by teaching you some vector addition and having you actually add the vectors to get an overall dipole. That'd be fun. I just figured if I did that, I'd scare away all the non-physics-y type. But it's good to add vectors. It's good for your health. The trick with it is there's 3-dimensional vectors, so then I'd have to teach you how to add vectors 3-dimensionally, and that's kind of a pain in the butt. And also, the dipole, the value of the dipole is not simply equal to the delta En. The delta En gives us an introduction to how to kind of think quickly on whether we have a dipole or not. the actual dipole moment has units of, oh goodness gracious, I'm not 100% sure, but again, for the physics people, because I know that a lot of you are taking the physics, the actual unit for the dipole would have to be, and it's a combination of electric field and distance or radius, right? So it has to have units of electric field and then the distance in which that electric field is kind of offset. You guys have just done your electric field unit, haven't you? You guys did your electric fields, right? So it's a combination of what that field is and how strong that electric field is, and then what that position of that electric field is with respect to the nuclei. So it's got radius units, it's got meters in there, it's got electric field units, which is, oh my goodness, do I even remember electric field units? That's magnetic field units. Epsilon is the symbol for electric field, but isn't it something like Coulomb? Oh, that's exciting. Electric field. It's force per unit charge, newtons per coulomb. Newtons per coulomb. Isn't it newtons per coulomb? Yeah, newtons per coulomb. So you'd have to have newtons per coulomb with a distance in there, and then the equation in order to calculate that from a delta En is ugly. It's an ugly equation. So it's not just as simple as adding vectors that are represented by a delta En. So it's not doable. So you're lucky it's not doable. But if you were actually, you know, doing the physics of it, you would calculate it that way. So again, I'm not going to spend a lot of time drawing up the 3D Lewis diagram. I'm hoping, my ultimate goal is that you guys look at NH3 and you think about it a little bit and you can come up with the shape. What do you think? What am I drawing here? NH3. I want to draw the 3D Lewis. What is NH3? What kind of shape is it going to be? See if we can do this in our minds. Yep. Yep. Trigonal pyramidal, triangular base pyramid. Coming from, because we know how to draw NH3, right? N, two dots, and then HHH. So that's 4, that's sp3 with one lone pair, trigonal pyramidal. If you're not able to do that and you've got to take all the steps, then by all means, you're taking all the steps. But for the sake of this lesson, I don't want to go through all those steps all the time. It'll take us forever. So I'm going to just draw it up. H, 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 lone pair. I'm pretty sure the delta En is greater than 0.2. So again, I want to kind of dispense with that. I want to get to the end so that I can give you some time to work. And I'm pretty sure that the N has the greater electronegativity. Is that correct? You can check that for me and make sure. Yes? So which way are my arrows pointing? Towards the N. So this way, plus, plus, plus. And this is not symmetrical. If we take away that bond on my CH4, all of them are slightly pointing up. They'll cancel each other away if we look at it straight on, but if we look at it on the edge, they're all slightly pointing up. What that does is it results in an overall dipole that goes right up the middle of the molecule, straight through where those lone pairs go, and I'm going to try to represent this. It's going to head up this way, like that. The overall dipole right up through the middle, if you were to add those three together. If that's a complicated picture, you don't have to add it, but you know what I mean? I don't know if you can. And that means, again, we've got delta positive, delta positive. In actual fact, the whole bottom of the molecule is positive, and the whole top of the molecule is slightly negative. If we were to add that notation, slightly negative, slightly positive. Okay? I'm not going to put any notation underneath there. Yes, there's polar bonds. It's non-symmetrical. Therefore, the dipoles do not cancel out. Therefore, we have an overall dipole. It is a polar molecule. All right? Now, when drawing this, for the sake of the ease of symmetry, the hydrogen seems to be the odd guy out. I'd put the hydrogen at the top of the tetrahedron if you're going ahead of me and drawing it, just because it makes it a little easier to think in terms of up and down. So I'd put carbon, and because there's only one hydrogen, I'd put the hydrogen there like that, and then I've got my tetrahedron here of my chlorines. So on my model, typically white is hydrogen, but just for the sake of changing just one out, I'll put a different color at the top of this guy. All right, so the purple in this one is the hydrogen. Again, we should calculate the delta ENs for both of them, all right? But I know that the CH has a delta EN greater than 0.2, also the CLC, and again, for the sake of time. And you're going to find that the carbon has a higher electronegativity than the hydrogen. So in this case, we've got this heading this way, right? The electrons are being pulled down. And you'll notice the chlorines have a higher electronegativity than the carbon. So this will head out this way, and this way, and this way. And even though it's a tetrahedron and it's a symmetrical shape, with the electrons being kind of pulled all in a downward fashion, we're going to have an overall dipole down, because our H isn't pointing up, and it wouldn't even be the same size as these dipoles. So in this case, it's pointing all the way down. Here's where it's going to get a little ugly, a little complicated. I guess we'll put it along this side. It's going to point like all the way down that molecule there, if we were to add those guys up. All right? Yeah, you could put it off to the side. It's a good idea. So in this case, our slightly negative end is down here, and our slightly positive end is down there, or up there. Okay. I don't have any other examples. Let's, oh, that's great sounding. Let's now just talk a little bit about how polarity can affect liquids. And then we're going to talk very briefly again about solubility. And we've talked about that last year. Again, it's very much kind of a review. So a liquid that contains polar molecules will be attracted to both negatively and positively charged rods, because the molecules are able to move and orient themselves so that their negative dipoles are closer to the positively charged rod, or their positive dipoles are closer to the negatively charged rod. Okay. And if you have a liquid, this is a test for polarity. And I've shown you this. I've shown you this with the stream of water. I've heard of other teachers getting other liquids and then demonstrating how they either can bend or not bend under the electrostatic attraction of a charged ebonite rod. I considered using ethanol, but if you get a discharge, if you get an electrostatic discharge close to the ethanol, it'll burst into flames, so I decided not to do that. And I don't think I have any other liquids that would react the way I would want them to react without bursting into flames, which isn't a good thing. Actually, you know what? It wouldn't be a bad idea to put here, right, test for polar liquids. Just kind of give it an official kind of title. Non-polar liquids won't react. The stream will just continue. And like I said, this is just what we've done in the past here. Right, so if I take a negative rod, and today the weather's great because it's very dry and very, the air is very dry, and I should be able to bend that like crazy. Woo, that's fun. Right into the, can I get it right into the thing? No. And if I use a positively charged rod, this positively charged rod, same action. It's actually even more, got even more strength. And then of course, as I've shown you in the past, my superpowers. And this is just fun. This is just for me now because you've all seen this. It makes me feel powerful. Oh, yeah. Ah, that's good stuff. All right. Zapped here because I got charged. All right. And in the textbook, that's just a picture that was in the old textbook. Actually, that's a couple of textbooks ago. It's a good picture. It's not a big deal. If you have a positively charged rod, nothing to draw here. Right, all the molecules, in this case the water molecules, will orient themselves so that the negative oxygen is close to the positively charged rod. The stream will bend. The entire stream bends because all of these water molecules are stuck together by hydrogen bonding, so the whole thing bends. And if you have a negative rod, they just reorient themselves so that the positive ends are attracted to the rod. Okay, so there's a little bit of homework on that. I still want to talk a little bit about polarity and solubility. So I've got another, not many slides. What have I got left? 17 of 21, so there's not very many of them left. Again, it's very much review. So I got a couple more things I want to talk about. So another important property that is affected by polarity is solubility. We again talked about solubility last year, and we would have talked about this type of solubility in the unit on solubility, right at the very beginning, where we talked about how different solvents can dissolve different solutes. And I had to write down the general rule, like dissolves like. And that makes reference to the solvent dissolving the solute. Polar solvents will dissolve polar solutes. And ionic counts as that, because ionic is really extreme polarity. Right? If you have sodium chloride instead of hydrogen chloride, it just means the delta En is, for the sodium chloride is greater than 1.7. It's like extreme polarity. So if you have something like water, water can dissolve HCl. Water can dissolve sodium chloride. So again, we're talking just general solubility. We're not talking like the KSP stuff that we did earlier on with the ionic solids. And obviously we can do those calculations. That's more quantitative. This is just kind of, a general type solubility rule that it's good to know and good to understand. Nonpolar solvents dissolve nonpolar solutes. Remember, nonpolar solvents include liquids that are derived from crude oil. Things like gasoline. That's what C8H18. And you can dissolve then I2, which is diatomic, nonpolar, no dipoles. I2 can dissolve very nicely in gasoline. Acetone counts as a nonpolar solvent. Right? Actually, I made a list for the grade 11s because we didn't really get into it very deeply, but I made a list of nonpolar solvents. And again, things that come from gasoline, or things that come from crude oil. So things like gasoline, or octane, we call it. Octane, C8H18. Acetone, right, which is nail polish remover. Again, dissolves non-polar substances, okay? Nail polish itself is a non-polar solid that's dissolved in acetone. So you put the nail polish on, the acetone evaporates away, you're left with the solid left on your fingernail, and then when you want to remove it, you reintroduce the solvent, which is non-polar, and it dissolves it away, all right? Other non-polar solvents, paint thinner, right? Paint thinner. And that has to do with what we would call oil-based paints, not necessarily latex paint. Latex paint is dissolved in water. Latex paint is a polar solvent, so you can clean it with water, all right? Substances that are non-polar that can dissolve in these non-polar solvents. Styrofoam is non-polar. Most plastics are non-polar, which is why you don't want to, maybe use acetone to remove that label from something that's plastic. Like, you've all encountered probably a label that you can't get off, right? You can't get the label off. Say maybe a glass something, and you're cleaning it. You put it in the water, and nothing comes off. That's because that rubber glue is probably non-polar. Use a little bit of acetone on it, and it'll take it off in no time. And that's great on glass. But if you were to try to take a label off of a piece of plastic, let's say, let's date myself, a CD case, and you used acetone to do that, you'd start to dissolve the plastic itself, and it would leave it wouldn't be shiny anymore because you've dissolved the top layer of the plastic with the acetone because it's non-polar as well. So plastics are non-polar. Okay. A couple of things that a couple of slides that I want to add to this. What if we have a molecule that has a polar end and a non-polar end? What's it going to dissolve in? Because carbons bonded to hydrogens tend to be non-polar. Again, carbon is going to be sp3 hybridized. It tends to be symmetrical. The hydrogens all point in opposite directions. The dipoles cancel out. So carbon compounds tend to be non-polar. Well, they are non-polar, the large carbon compounds. And then if we stick an OH on the end, like in an alcohol, and this, by the way, is methanol. This is methanol. If you stick an OH on the end, now you have a polar region, because there's going to be a dipole in this thing that's going to pull the electrons over here. This is going to be slightly negative. This is going to be slightly positive. This is going to be non-polar because these dipoles are going to cancel out. It may have a small little degree of polarity because it is slightly it's got a slightly trigonal planar shape, but it's not very polar. Those little tiny dipoles there really don't add up to much. So you might ask, what's it going to dissolve in? In this case, when you have a small nonpolar region, and in this case a large polar region, and when you see the words small and large, you're going to say, wait a minute, this thing's a lot bigger than this. What we mean by small versus large is kind of its degree of influence on the molecule. One single C compared to an OH, this dipole is so strong that the non-polarity of this isn't going to have a chance to outbattle that. This stuff is going to be soluble in water. It's also combustible, but it will be soluble in water. Okay? This methanol is also known as methyl hydrate. You can buy this in little containers, and you can put it in your gas in the winter if some condensation causes some water to get into your gas. and it'll sit at the bottom of the gas tank. And if you get down to the bottom of the gas tank in the winter, sometimes you'll grab up some of that water that's sitting at the bottom of the gas tank, and your car will not run very well. It might not run at all. But if you add a little bit of methanol into it, what happens is the methanol dissolves in the water, and it sticks to the water, and because it's flammable, if it gets into the engine, it goes into the engine with some water, and the methanol part burns, allows the engine to keep running, and then the rest of the water gets heated and ejected out of the back end of the, of the tailpipe. So methyl hydrate can grab up the water in your gas tank because it's soluble in it. It's combustible, so it can burn in your engine, and then it can get that water out of the gas tank. So because it's soluble in water, it's useful in that way. Now, what if we had an alcohol, and that's what these molecules are called that have OH groups on the end. These are not hydroxides. What if we have an alcohol then that has many carbons in a row, a long chain of carbons? And we're kind of starting to look ahead to our next unit, which is organic chemistry. And that's really why I'm telling you this stuff right now, so that when I get to the organic chemistry part, and I start talking about polarity and the polarity of molecules and whether it's soluble in water or soluble in something like gasoline, you've already got a background on it. Again, I'm still going to have the delta negative and the delta positive, but due to the large number of carbons, London forces are going to dominate this. Remember, if something is going to dissolve in water, it needs to be almost surrounded by a little, pocket of water molecules. We saw that in grade 11 when we talked about dissolving salts in water. We talked about a sphere of hydration. So if water is going to try to, say, engulf this molecule in other water molecules, because that's what successful dissolving is, it's not going to do very well. Yeah, again, there's going to be a delta negative and a delta positive, and there might be a handful of water molecules that might stick to the end of this molecule here, but due to the fact that there's no charges on this, this is symmetrical, this is nonpolar, the water molecules are not going to be attracted to that. There's going to be no interest in that end of the molecule, and so this molecule will not be able to be surrounded by other water molecules. Unsuccessful dissolving. It will not be able to be engulfed in the water because this end has no interest in water molecules being attracted to them, or vice versa, however we want to say it. So as your carbon group gets larger, it becomes less soluble in water and more soluble in a non-polar solvent. Non-polar solvents have no interest in this end, but they can snuggle up very closely to this part of the molecule because it's exactly the same type of molecule. A non-polar solvent, like gasoline, can surround this molecule greatly and engulf it into its liquid and therefore dissolve it. Now, I'm not gonna give you something like 3. Oh, is it soluble? It's a progression, right? I'm not gonna make you tell me is it soluble or not and give you one that has 3 carbons. And is 4 the starting point for where it isn't soluble? Not necessarily. It's a slow decline in solubility in water. It becomes less and less and less soluble in water, right? We could actually calculate a K, the KSP for certain alcohols in water, and you would get less and less and less and less and less and less and less, right? So, more carbons, less soluble in water, more soluble in nonpolar substance. So don't write this down. This is one of these that let's just discuss it, and then we've got it and we're in good shape. So determine whether water or benzene. Benzene is C6H6, very nonpolar. So essentially this is polar and this is nonpolar. Which would dissolve it better? So you know what I'm really asking you here in this question? I'm asking you whether the molecule is counted as being polar or nonpolar. Because if it's polar, it's going to go into the water, and if it's nonpolar, it's going to go into the benzene. So HF, how would you count that? Is it a polar molecule or nonpolar? Yeah, it's polar. The delta En is quite large. It's one of the larger ones for a molecule. This is polar, so this is going to go into the water. So I'll just put here water, H2O. B, something that has like 20 C's and 42 H's. Nonpolar, right? It's going to be a big long chain, but it's going to be very symmetrical. It's going to cancel out. This is going to go into benzene, C6H6. CH3OH. What do you think? What's it going to be? Yeah, it's polar. It's only got one C, which is the nonpolar part, but it's got the OH on it, which is a polar region. This is going to dissolve better in water, H2O. NaCl, what's it going to dissolve in? Yeah, it's going to dissolve in water. It's ionic. So it's super polar, essentially, H2O. C8H17, and then with an OH on the end. Yeah, benzene, it's nonpolar. Because of the large nonpolar region on it, that OH on the end doesn't have a chance to really dissolve in water. If I were to put water nearby it, it might stick to that end, but it wouldn't be able to engulf the entire molecule to dissolve it. So C6H6 is the solvent there. I2, yep, it's nonpolar, it's just two I's. C6H6, C6H6, and grease. What's that? I didn't hear anybody. I couldn't hear. Yeah, it's benzene. Grease comes from crude oil. It's made up of a whole mixture of these nonpolar molecules, and therefore C6H6. Okay? So just a little review of polarity, and to put on the end there, solubility, and that really is in more benefit for what we're going to be doing in the next unit. And that's the end. There's no actual questions on that. And you've got a handful of questions to do